on where we were. So we're going to just finish this up, finish this module up, wrap up this exam 1 information. So remember, we talked about at the very, like a month ago, precipitation. Remember, Q is just the same process as K, it's just not necessarily at equilibrium. So if Q equals K, that's going to be a saturated solution, right? That's at our equilibrium, it's saturated. The maximum amount is dissolved. If Q is less than K, it's unsaturated, so nothing will settle out, right? So there won't be a precipitation. If Q is greater than K, then we're above the saturation point, and that means we're going to have an insoluble solid that's going to settle to the bottom. So we need to remember these, because what we're going to do now is we're going to figure out, will something precipitate or won't it? Okay, so now for our first question, will a precipitate form when we mix lead 2 nitrate with sodium bromide if the concentrations before mixing are 0.01 molar and 0.035 molar respectively? Okay, so when we're going to do this one, the first we need to figure out is, what do we have here, right? So this is our overall reaction. And if we look at what our overall reaction is, there's 2 pieces in here, right? Because we have both lead nitrate and sodium bromide. But really, it's that lead and that bromine that are adding to the lead 2 bromide, right? Because this is what we want to figure out. That is our precipitate. So we want to see if it will form. So the lead is just going to be the 0.015, because we only care about the lead, right? And the bromine is just this piece, right? So we have a little bit of these. So we need to figure out PbBr2. So we'd either look at a table, or I would give you the KSP for PBr2. So one of those 2 would occur. Okay, so we're looking for PBr2, I can talk, lead 2 bromide. So the overall equation is what leads to this. So this is the equation we're talking about, right? Because we want to know if we're going to get a solid. So when we do our Q, right? So when we do our Q is just going to be Pb2 plus times Br minus squared, right? Remember, when we do Q or K, products raised to the coefficient over reactants. Reactant is a solid, so we don't put it in. Right, so then all we need to do is put in the numbers they've given us. Because remember, when you have an equilibrium or a Q, a K or a Q expression here, an equilibrium expression, you need to make sure these are in molarities. They are in molarities, so all we have to do is put them in. Which, I know I have this meter, I just looked. And here it is, meter. So here's our Q. That's wrong. This is our Q. I just can't fix it. So that's our Q. If we look at what our K was, here is our K. So our Q is greater than our K. So that means, will it precipitate? Yes, it will precipitate. Because Q is greater than K. So indeed, yes, it will precipitate. Okay, so now let's try another one. All right, so we want to know, will it precipitate again? So we have calcium nitrate and sodium hydroxide, and the concentrations of both are 0.015. Okay, so here's our KSP of calcium hydroxide. So that's what we're going to compare our Q to. So the question is Q greater than K, right? That's our question. So that's our K that we're going to keep our eye on. Here's our overall reaction. But again, this reaction doesn't really mean anything to us, because what we care about is the calcium and the hydroxide, right? And remember, the concentration of both of them are 0.0175. So 0.0175, 0.0175, same concentration. Okay, now, again, we've got our K, that's what we're going to compare it to. Our overall reaction that we care about, again, is this solid, the calcium hydroxide. So when we write our expression, It's almost the exact expression that we just did. So it's going to be Ca, again, the molarity of, and then OH, and we have to square it because remember, products raised to the coefficient over reactants, but that's a solid. So we just plug in the 0.0175s, which I have this all right here for you. We get Q is 5.36 times 10 to the negative 6. So we compare that to our K. So is our Q bigger than our K? I mean, barely, but Q is bigger than K. Yes, so it will precipitate. Right, so the keys to these, make sure you know what solid you're talking about. Make sure you write the reaction of that solid because that is going to give you that equilibrium expression, right? That we need to write. Products raised to the coefficients over the reactants. Okay, so now let's try some fun ones. So we got our basics, our basis here, right? Let's try doing some fun ones now. By the way, let me know if you have any questions when we're doing these. I can always go back. Okay, what's the minimum amount of hydroxide necessary to just begin to precipitate magnesium if the concentration of magnesium is 0.059 in seawater? And there's our KSP. Okay. So, and that's a KSP, by the way, for magnesium hydroxide. Okay, so they're asking about, they gave us the KSP here for magnesium hydroxide. And so the question is, what's the minimum amount of OH needed to just precipitate magnesium when the magnesium has this concentration? Forgot the 9. Right, so what is OH? And they gave us our K here. And remember, when something precipitates, that's right when Q equals K. That's when it's going to start precipitating, right? So when Q equals K, that means it's going to start precipitating. So we want to know at what point does Q equal K? So we write our equilibrium expression using our reaction, which again, OH squared times magnesium. So this time we have our Q. We know our magnesium, right? By the way, because Q is K. Q is K, so this is our K because Q equals K. And we know our magnesium concentration, right? It's 0.059 times OH squared, right? So we just divide by 0.59, divide by 0.059, and then we just take the square root. And that is going to give us our OH. And again, this is going to be the concentration of OH. I'm just moving my computer down here. That's going to be our concentration, of OH just when it begins to precipitate, right? So at what point will it begin to precipitate? So, and when you do this, I think I have this neater here. I do. You get the concentration of OH is equal to 1.9 times 10 to the negative 6. So that is the molarity. So the minimum molarity for OH is 1.9 times 10 to the minus 6 molar. And here again, it's the exact same thing, I just made it look prettier. Right, so here it is. Here's our end piece here. Again, the key here, you need to write this reaction because that's what's going to give you your Q. Your Q is K because when something begins to precipitate, that's when Q equals K, right? Right above that amount, right? Whatever is above that will precipitate out. All right. Questions on this one? We're going to keep increasing the difficulty with every question from now on. But they're the same basis here for what we're doing with our Q's and our K's. Okay, here's a fun one. What is the minimum concentration of calcium nitrate that will precipitate calcium hydroxide from a 0.0175 molar NaOH? Okay, what? So what do we have here? Okay, so we have calcium nitrate and sodium hydroxide. That's our solid, right? So our overall reaction is calcium nitrate, sodium hydroxide, potassium hydroxide, right? But this is what we care about, right? This is what we care about. But when we look at this, right, our overall reaction that we care about is this reaction right here. So again, when we precipitate, Q is K, and we know how much OH we have because it says from this much NaOH. So we already know what our what our OH concentration is, right? It told us. So when we do this here, this concentration is our OH, right? So, which is this piece right here. And remember, Q equals K. Our Q is just going to be 4.68 times 10 to the negative 6 equals, don't know what Ca is, times 0.0175 squared. And then we just solve for our calcium, right? Okay. So I have this math nice and pretty here that I did for you earlier. Here it is, much prettier. There we are. So we just solve for our calcium. And so remember, when calcium is 1.53 times 10 negative 2, that's calcium nitrate, right? Same, it's just a net ionic piece of it, but that means that is the concentration of this whole thing. So when it says like, what's the minimum concentration of calcium nitrate? We don't really need the calcium nitrate. That's the nitrates are just spectator ions here, right? So what we're really talking about is the calcium, right? Because if we broke these off, those would cross right out, right? Here's all we're left with our net ionic here. So that's why this is this. If you remember that from a long time ago, right? When we did these in intro chem. And you might have done them in 219 also. Okay, any questions on these? No? Okay, I'm gonna believe you because it's gonna get really fun now. Okay. What is the magnesium 2 plus concentrate? What is the concentration of magnesium 2 plus when 0.011 molar calcium 2 plus just begins to precipitate from seawater? Okay, so they gave us the KSP of calcium hydroxide, but they're asking for magnesium. So they're asking for magnesium, but they're giving us calcium. Well, what do we have here? We have the concentration of calcium. So if we have the concentration of calcium, we could solve for the concentration of hydroxide, right? And then we could use that concentration of hydroxide to find magnesium because magnesium hydroxide is another one we can use. Right, so the question is, what's the magnesium concentration when calcium just begins to precipitate from seawater? So we can find out the concentration of this hydroxide here, use it here, solve for magnesium. Because remember, when it begins to precipitate, that means Q equals K. So that's kind of our plan. Let's see how this works. So Q equals K. So we have to use, again, how do we know which one we're using? Because this is the constant they gave us. So this is how we know which one we're using. So we write our equilibrium expression just like we did before. Now what we're going to do is we're going to solve for OH. We have Ca. We have our Q, because remember, Q equals K. So Q is K in this case because it's beginning to precipitate. And then all we're going to do, solve for OH. So this piece right here, we've now done this 3 times. So we've done the same piece 3 different times now. So here's our concentration of OH when calcium begins to precipitate, right? So this is OH when calcium begins to precipitate. But the question is, what's the concentration of magnesium at this point in time? Well, if we know OH, we can use it to solve for magnesium. All we need is the KSP of magnesium, which I'm going to give you in a second. All right, just making sure everyone has time to write this piece down here. Okay, so here we are, here it is. We don't really need this piece right here. So here is what we got from our last answer, right? 2.06 times 10 to the negative 2. So calcium begins to precipitate when OH is 2.06 times 10 to the negative 2, right? So now what we're going to do is we're going to use this for our OH. We know magnesium, which I'm going to have to give it to you, and then we're going to use that to solve for our Mg. So writing our equilibrium expression, and again, Q is K. And so when we do that, we just solve for, let me just write all the math here, right? So we have our magnesium, 0.011 is our Q is our K here. And now remember this one is OH squared. So, right, we're gonna have to divide by 0.011, divide by 0.011, and then take the square root of our answer. And that is going to give us our, oh my gosh, I just totally did that backwards. Yep, did anybody ever notice that, what I just did right there? I plugged it in for OH, and I plugged it in for magnesium instead of OH. Let's try that one more time. Q equals, we don't know magnesium. We do know OH, 2.06. No square root needed this time. No square root needed, right? And so then all we have to do, square that, divide it. Magnesium 2 plus equals 2.06. I'm not sure what's going on with my pen. Give me a second, let's try this again.
Are you dividing that by the KSP?
Yes.
Oh, okay, okay.
Yes. Sorry, my pen is only writing half of what I'm writing right now here. So remember, Q is going to equal our KSP. Let me just try it up here and maybe. Nope. Okay. Oh, okay. Yeah, there we go. I'll just write down here. So we have. All right. My pen's not working right now. I'm just going to have to show you the math. But I already have it solved. I'll see if I can do this in this next piece. Oh, it's okay. So when the Q equals K, and then we're going to solve for our Mg. Now it works. And so we plug in our OH right here. So we plug in our OH, solve for our magnesium. And so when calcium just starts to precipitate, the concentration of hydroxide is 2.06, right? At that point, magnesium's concentration is 4 times 10 to the 8th to the minus 10th, right? So if you remember magnesium in seawater from 2 pieces ago, it was 0.059, I think. So magnesium's solubility went down from 0.059, the concentration, all the way down to here when we added the calcium hydroxide. Okay, so let's go back to the beginning of this one just so I can explain it one more time, because it's kind of 2 places in one. Okay, so the first thing we did, so they're asking about magnesium, but we have the information about calcium. Now here's the KSP for calcium hydroxide, right? Because we're talking about calcium hydroxide. So we have our equation, here's our Q, right? We have our calcium, we're gonna solve for OH. So we solve for OH just like we did before. Now we're gonna use this OH concentration. So that's our KSP for CaOH. Here's our KSP for MgOH, right? So now we're going to solve for Mg and we're going to use that concentration of OH that we just found. And again, our KSP here is MgOH2, which usually will be given to you. It'll be like, hey, here's the KSP. So our first KSP we had to use for calcium hydroxide. Our second KSP, because your KSPs have to match your equation. So any questions on this one? It's a lot. So I want to make sure if anybody has any question, please let me know.
Why'd you cross out the precipitating Mg2 plus begins when OH, the 1.910 times 10 to the negative 6?
Oh, we just didn't need it. That's just like extra information.
Oh, okay.
Yeah, that was just extra information. That's why I crossed it out. It doesn't help us with this problem. It's just like nice to see. Any other questions on this? Okay, so now, a lot of times when we're doing these problems, people are like, oh, I don't know, like which one should I use? That's where this little KSP table comes in. It's kind of a handy dandy table. So this is the same type of problem. I just didn't give you any KSPs this time. Okay, so a solution is made by mixing lead 2 nitrate with silver nitrate. So both compounds have a concentration of 0.01 molar. Sodium chloride is added to precipitate out both silver chloride and lead 2 chloride. Okay. What is the silver concentration when the lead 2 plus begins to precipitate? So super similar to what we just did, but we have to find our KSPs now because I'm not going to give them to you. So we think, what's our reaction? PbNO3 2 plus Ag. It's actually not our reaction. I'm going to write this smaller so I can put both of these in here. PbNO3 2. And we have Ag NO3, right? And both these are 0.001. So NaCl is added. Sorry, it's really messy. To make PbCl2. I'll have this neater on the next slide, you know that. And NaCl is added to make AgCl, right? Both of those are solid. So we're going to be using this one and our silver, why can't I find it? There it is. Those are our two KSPs we're going to be using. Okay, because those are our two solids. And remember, so the amount of PB we have is 0.001, and the amount of AG we have is 0.001, but who knows how much NaCl we have? We don't know. We don't know how much Cl we have. Don't know, right? Because it just says they added. And again, the Na means nothing to us, right? So it's pretty much, this is what we have here. They added Cl. We don't know how much Cl we've got. Okay, so let's try this one. So here's our overall reaction. So once the Ag plus concentration, when Pb2 plus just begins to precipitate. Well, that means we're going to we need to find PbCl2 first. So here's our overall reaction. Remembering, when something precipitates, that means Q equals K, right? Just above that. When we do our Q, our equilibrium expression, it's just going to be Pb times Cl squared. We found out that our Q from the, we just looked at our PbCl, our KSP from the table that we just looked at, right, was 1.17 times 10 to the negative 5. That's our KSPV, or our KSP for PbCl2, right? And when we look at this, we have the concentration of Pb. We have this one. We're just going to solve for that one. So we have this. We have this. We just need to solve for this, right? So our Q, which is K, is 1.17 times 10 to the negative 5 equals, we have our Pb times Cl squared. So just divide by 0.001. That's too many zeros. And take the square root. And Cl minus equals 1.08 times 10 to the negative 1. So that is our Cl concentration. So everyone's good on this setup here. Any questions on this? Here it is neater. So now this is our Cl minus. And so now our next piece is we're going to be using AgCl, right? And we want to know the Ag concentration. So we're going to use our KSP, that's AgCl, which I do not remember what it is right now. Right, we're going to use that KSP that we found on the table. Here's our Cl. We're just going to solve for Ag. So it's, again, the same kind of question, just a little piggyback. And this time you had to find the KSPs. They weren't just given to you, right? You had to find them on the table. So here's the number that we're going to use. We don't need this one again. This one's just extra information. Our KSP for AgCl is 1.77 times 10 to the negative 10. That's our KSP. So we just plug it in. 1.77 times 10 to the negative 10th times Ag, which we don't know, but we know our Cl, we just solved for it. Right, and then Ag equals 1.6 times 10 to the negative 9th molar. Okay. Questions on this one? Let me show you neater math here. So we did two of these very similar to each other. There are like it's a little bit more, but as long as we have our, like what we're trying to do, remember, it's a piggyback problem. You find one answer and then use that answer and plug it into the next one, right? So you use one to do the other, to find the other. Questions on this? We're good on these? Okay, so that's KSPs, and we did molar solubilities last time. So now we're going to do some complex ions. So we're going to do a little complex ions now, and then we're going to do more complex ions in another module also. So complex ions are something that we've been dealing with in lab for a while now, right? So it's all these transition metals that we've been dealing with. Remember when we talk about Lewis acids and Lewis bases, right? Electron pair acceptors and donors. So transition metals are usually pretty good Lewis acids, and they often bond to water molecules to form a hydrated ion. Water is a Lewis base. It's a pretty good Lewis base. It donates the electron pairs to form the bonds that we're talking about. So here's, for example, what happens when we put a silver. So this is the complex ion that we have. And so the complex ion of a neutral molecule, this is our complex ion here, this entire thing. But the thing that's attached is called a ligand. So the ion itself is this, but the thing that's attached to this, there's two waters that are attached to the silver. Water is what we call the ligand. Right? So we have complex ions, which is the whole thing, and the thing that's attached, we call it the ligand. So the one that we have a lot in our lab is ammonia, right? We're always, if you look, a lot of our complex ions are with ammonia. It's because ammonia is a really, really good ligand. So if a ligand is added to a solution that forms a stronger bond than the ligand that's already bonded, it'll replace it. So ammonia is a better ligand than water, which means that silver would much rather be with ammonia than it would be with water. So when you have silver, when you put silver in water and then you add ammonia, water gets kicked right out. And then silver will form a complex with ammonia because, again, it's a better Lewis base than water is. And usually, by the way, we don't even usually include water. We just kind of ignore it. So here's the exact, so this is this. Just look at what the difference is here. We just took out these waters. See, we just took out these waters here, and then we took out the waters here. And again, usually we don't write water in there because water is always a complex ion with whatever it's with. So we just ignore it completely. Now, when we write, sorry, we went too far. Well, it's not letting me go back. That's okay. So now if we're going to write a formation reaction for this, so like how does this complex ion form? It's silver plus ammonia makes this complex. So this is going to be KF, but again, KF is the same as KC, KA, KB, KSP, K everything, right? Products over reactants raised to the coefficients. So in this case, products over the reactants raised to the coefficients. And we call this KF the formation constant. So it's a formation constant of a complex ion. Okay, so now this is going to have a bunch of tables, and you're going to see these complex ions have gigantic formation constants, which means this very, very favorable. Remember from chapter 14, the bigger the K is, the more product favored it is. So when we were doing our KSPs, right, they were all super small, 10 to the negative 10th, negative 5th, negative 15th, right? Because those were reactant favored equilibrium constants. These are very product favored, like super product favored. Like you can see the best ligands have the highest formation constant. Like look at CN, look at how high these are. CN very high. Go to ammonia, look at ammonia 10 to the 8th. Look at this ammonia, 33, very high, right? A lot of these ammonias are very high. There's another CN, cyanide, very good looking if you can tell. So most of these are very highly favored. But again, when we use these, it's very similar to how we've used them before. We just have just a little bit more specifics on what we need to do. So for example, let's say we have copper nitrate mixed with ammonia, right? So copper nitrate mixed with ammonia. So the question is, how do you know what kind of complex ion it will form? Okay, so what I suggest is you go back to here, copper nitrate. So that's copper and ammonia. Because, right, nitrate's the spectator, it never does anything. It's this one right here. Right? So this reaction, it's going to be a copper plus 4 NH3s makes a Cu NH3 4 2+. Right? So that's how you figure out your overall reaction. You look at the formation constant to figure out which one it will make, right? How would you know it's 4, right? After you do a few of them, you kind of figure it out. But at the beginning, you look at your KF. Okay, so we've decided here is our reaction. So products over coefficients, don't forget, we're going to have to, now that one's not going to be super fun math, but that's okay. Now, remember, whenever you have an equilibrium expression, this means concentration of. Concentration is molarity. So we need the molarity of these things, right? So we want to know this. We want to know Cu. So we need to figure out the molarity of these things, right? Well, remember what we have here. So we have 200 milliliters of this molarity of our Cu. So we have 200 milliliters of 1.5 times 10 to the negative 3 molar. That's a 3. And of our NH3, we've got 0.2 0.2 molar, 250 milliliters, right? That's what we had before, but now we've mixed them together. So this volume is additive now because they're in the same container, right? So we have to take into account the volume is additive. So remember, we need to find our moles over liter. So we can find the moles of this, right? Because and I'm sure you learned this before, if molarity is moles over liter, then molarity times liters equals moles, right? So that means that this molarity, 1.5 times 10 to the negative 3 times 0.2 liters, that'll give us our moles of our Cu, and then our volume is additive. So our volume is 450, right? So when we do that, we need to take into account all of those. So here I am just doing that all in one piece right here. Here's our copper, again, before we've done anything. Here's our copper before we've done anything. And we do the same thing with ammonia. So we need to get the molarity of them because we can't put anything in here until we have a molarity, right? And we don't have their molarities because we had them in individual beakers. Well, now they're together. So now we need to know what the molarity is. We need to take into account that extra volume on the bottom, right? Okay, so first thing, okay, got our molarities. Now we can start our problem. So now that we have our molarities, we can start. Everyone's good on the molarities, yes? Okay, so now we have both of these. So when we're doing this, we want to know the Cu at equilibrium. So it looks like we're going to use up this Cu first, right? we look at these molarities, there's less of this. Probably going to use that one up first. So we put this into an ICE table now. So we put our values that we just got into an ICE table. And so let's look at this. So we have 0.11 and, well, that's going to stay in exponential form. Now, we started with this much. So everybody's good where we got these molarities, right? Those were the molarities we just calculated, right? So now our Cu is going to go down by this much. Our NH3 is going to go down by 4. And again, it's because of this, remember? This should bring you back to the first day of class. This concept right here where there's 4 of these, it goes down by 4 of these, is from the very first day of class when we started equilibrium, right? And then this is going to go up by 1. And again, these are coming from the stoichiometric coefficients. And the reason why I'm using this one is because this one is smaller, so this one's going to go away quicker, right? Limiting reactants, right? So that's why I chose the Cu here. That's where the change is going to come into. And I'm going to assume that all the Cu is going to get used up. And I'm going to assume all the Cu is going to be converted to the complex ion. That's my assumption. So, you know, when we're in lab and you'll come up to me and I'll be like, add some more sodium hydroxide, right? So what I'm trying to do is I'm forcing this to form, and this one's usually always going to be in excess. So it's always just going to be extra sodium hydroxide. I'm just trying to force your reaction to go over to products. Okay, so then we get our changes. And again, like this doesn't really even change anything because again, it's such a small change. So when we do that, we get our equilibrium. So here we are. And then we just plug these in and we're going to solve for Cu. It's going to be very, 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 very tiny, right? Very tiny. So when we do that, again, let me see if I can fit all this math on here. So we plug this in. Here's where our 6.7 times 10 to the negative 4th will go. Our NH3 ends up being 0.11. It's not going to really change. And this is what we're going to solve for. Again, it's going to be super, super tiny. And so when we do this, you get here's our Kf, which again belongs to that. You get 2.7 times 10 to the negative 13th. Very small. And so we just did an ICE table, so we need to check our X is small. But if we look at our original, we started with the original amount of Cu we started with 6.7 times 10 to the negative 4. Our K, we get 10 to the negative 13th. Like the approximation is always valid. You don't even need to check on these. It always works. All right, so this is just an example of how to use these complex ions. I'm going to skip the next one really quick and we'll come back to it later if we have a chance, because I want to talk to you about KSP and KF together. So these are KF, right? Formations, something's forming. KSP, right? Those are different. That's a solid. We're talking about a solid. So KFs are complex ions. KSP, we're talking about solubility. Something is a solid. So now, if you have if we're talking about the solubility of an ionic compound, right? We have a metal cation that's forming a complex ion, right? So now when we look at this, so let's just look at this. Here's AgCl, KSP. Again, KSP means we're talking about a solid. This is a formation of a complex ion. So in that case, this is a KF. Right? And so a lot of times what we'll want to do is, and this is, some of you have actually seen you bring up your test tube in lab and I'm like, hey, try adding this, right? And I'll look in my book. And what I'm looking to do is I'm trying to figure out which way I want to throw your equilibrium in your equation, right? And so sometimes I'll be like, add some NH3. And you'll be like, okay, right? And so like, for example, when I tell you to add sodium hydroxide, in this case, adding the NH3 to a solution increases the solubility of Ag+. And so sometimes I'll ask you to add an acid, and we'll talk about why that is as we go in class 2. So it just depends on which way you want to do the solubility. So now, what about if I have a question and I'm asking you about this equation? Let's just look at this real quick. I don't want to put the CL minus there. That's going to drive me crazy. Okay, so what if I give you like a mathematical question or ICE table or a molar solubility, and I'm like, and I ask you about this equation right here. How do you find the K of that equation?
Would you just times the KSP and the KF together?
Yeah, so remember when we did that, the middle-ish of chapter 14, right? So if you want the K for this equation right here, remember if you add equations, you multiply the Ks. So you would just take KSP times KF, and that's going to give you the K for this equation, right? So we're using that stuff that we did way back when. Keep it in your brain, because I'm probably not going to give you a super easy equation to do this with on your exam, but I might give you an equation with this, and you're going to have to do something like that, right? Same principle. It's just now it's a piece of a bigger problem. So just keep your mind that that can happen. Don't forget, again, beginning of chapter 14. Okay, so now here's what we just did. I was just showing you. And so we do this a lot. So we have AgCl as a solid, right? And we want to, if we add our sodium hydroxide or ammonia, same thing. Remember, we've talked about that same thing. That's how we make this lovely complex ion, right? Okay. So now let's talk about some other metals. And some of you, we actually were doing this today in lab. Some of you guys some of you on the Monday lab. So some of our metal hydroxides are amphoteric. Remember, amphoteric means that it's both it can act as an acid and it can act as a base. It can do both. So many metal hydroxides are insoluble, right? But they become soluble in acidic solution, right? We talked about how you can shift it one way or the other using Le Chatelier's principle. So if you remove OH or add acid, then you can make it more soluble. But some metal hydroxide also become more soluble in basic solutions, because what they do is they form a complex ion. And this is what we mean by they're amphoteric. So some of these metals in water are insoluble, but if it's in an acidic situation, they are soluble, or if it's in a basic situation, they're soluble. So that's why, for example, in some of those metals that do that, aluminum, chromium, zinc, lead, and FB, right? So that's why some of you in lab, right, I'll be like, add some ammonium hydroxide. I'm like, that's not working. I'm like, okay, let's try adding some acid. I'm trying to figure out where that precipitate's coming out, right? Trying to get in the middle. If we can get to a pH neutral, maybe we can get our precipitate. Or another way, trying to get the complex ion to form, we might add one or the other to do that. And so when we're doing these, when you see these and we're going back and forth, it could be the fact that we're dealing with one of these hydroxides, right? And we're either trying to make it more soluble or less soluble, depending on what we're adding. So remember, aluminum 3+ is acidic, remember, because highly charged metal cations are acidic. Remember that from our I don't even know when that was. It was a while ago, right? When we were doing like acids and bases, or sorry, salts, if they're acidic or basic. Highly charged metal cations are acidic. Now, why? Why are highly charged metal cations acidic? They are acidic because of these complex ions they form. All right, so when it loses a water, so you can see here, it becomes acidic. And if you add OH, so if we add hydroxide to this, so if we add a base to this, it's going to drive this equilibrium to the right. And it's going to continue to remove H's from the water. So you see here, see how this is water 6, this is water 5, and now it's an OH. So it took an H off, right? And remember, I wrote H3O plus, but it might be easier for you just to see if it's an H. But again, remember, H doesn't actually exist. It's really H3O plus. But if you keep doing this, right, we're gonna have 5 waters, and then we'll have 4 waters and an OH, 3 and an OH. I want you to look at this one right here. Take out the water here. You've got Al, OH, 3, right? An insoluble product again, right? So aluminum is one of those that goes back and forth. So what does that look like? So you can see in a pH neutral situation, we have the complex ion, which is the same thing as just aluminum hydroxide, right? Remember, because we take the water out. We don't write water because water is always there. So as chemists, we just ignore water all the time. But if we have an acidic solution, that's our highly charged metal cation, right, which is forming a complex ion with water. And in basic solution, again, it's also making a complex ion, this time with water, and it's soluble. So some of these, which let me go back to some of these that are, some of these ions are insoluble at a pH 7, but they become soluble either in acidic or basic conditions. And again, that's a lot of what we're doing in our lab with trying to get our precipitates. Okay, so that is our exam 1 material. We've done it all. All right, any